Hello everyone, and welcome to another video on the chemistry of benzene. This is one of a series of videos based on chapter 16 of McMurray, and as a reminder, you do have a scanned copy of this chapter on Blackboard. This video will be focusing on the substituent effects in aromatic rings. Basically, the reactions we looked at in previous videos were the substitution of a benzene ring. And what happens if you have a benzene ring that has already one substituent and you want to add a second or even a third one? Where will those extra substituents go? And that is the focus of this video. So when you have a benzene ring that has already one substituent that I'm going to call A, and you want to add another substituent that we can call B, where will it go? Will it go in this position, or in this one, or in this one? And as a reminder, or as a new piece of information, if you don't know, the different positions of a benzene ring are called ortho, meta, and para. So if you have a substituted benzene, this would be the ortho position, these two. This would be the meta position, two meta positions, and one para position. So where will our substituent B go? Well, the answer is it depends. It depends on the nature of A. First of all, how fast the reaction will be. Will it be easier than if you had only benzene, or it will be more difficult? Well, it will depend. We have some groups that will be activating. The reaction would go faster than if you had benzene on its own, and others would be the activators. The reaction will go more slowly than if you were comparing a similar reaction but having a benzene ring with no substituents. And where it goes, ortho, meta, or para position? Well, you will have ortho and para directing groups, and ortho and para and meta directing groups. So as you can see, it is not very complex, but there are a few things that we need to consider, which is the nature. Basically, it will all depend on the nature of the substituent A. So if you imagine we compare everything to the reactivity of benzene, electrophilic substitution in a benzene ring with no substituent, you will have certain groups that will favor ortho and para position. That's what we call them ortho and para directing, and it will be activating. The reaction will happen more easily than if you were trying to do this reaction in a benzene ring on its own. You also have the activators, and those are benzene derivatives, in which the reaction will happen with more difficulty, slower, than if you had a benzene ring on its own. And among those, the activators, you have the ones that favor a product that will appear in ortho and para position, and you have others that will favor that second substituent going into a meta position. So activators and the activators is comparing the reactivity of that substitute benzene with the reactivity that benzene would have on its own. And ortho and para and meta directing focuses on where that second substituent go, either in an ortho and para position or in a meta position. And we will look at why that happens, why sometimes ortho and para and sometimes meta. And that is determined by the first substituent, the one that is already in that benzene ring. And it's determined by the stability of the carbocation, the Whelan intermediate that you are forming on each case. So, the substituent effects. There can be inductive effects and resonance effect. And inductive effects are when the substituent withdraws or donates electrons to the benzene ring through a sigma bond. And a resonance effect is when your substituent withdraws or donates electrons through a pi bond to the benzene ring. So for example, inductive effects. Inductive effects depend on the electronegativity and the polarity of the bonds in the functional groups. And here we've got examples of halogens. We've got an example with a carbonyl group in a ketone, a nitrile group, or a NO2, a nitro group. And if you think of the separation of charges, for example, in a halogen, halogens have a partial negative charge. That means that this carbon here has a partial positive charge, and there is a withdrawing of electronic charge from the benzene ring, from this aromatic ring, towards the halogen. In the case of a carbonyl group, you have the oxygen with a partial negative charge, you have the carbon with a partial positive charge, and again there is a withdrawing of charge from the benzene ring and into the substituent. With the same with the nitrile group, if you look at the separation of charges, you have the nitrogen has a partial negative charge and the carbon a partial positive charge. And again, that determines that the way the electrons flow, they are being pulled from the benzene ring and into the substituent. And finally, a nitro group. Again, well, in this case, it's not a partial positive charge; it's a proper positive charge of the nitrogen. That means again that sort of pulling, withdrawing of electrons from the benzene ring and into the substituent, and that withdrawing of electron happens through a sigma bond. So there are we're not looking at the pi skeleton. Is withdrawing from the sigma bond between the carbon of the benzene attached to the functional group. Alkyl groups donate electrons, so by again an inductive effect. So in this case, is the carbon donates a certain amount of charge to the structure, and it's an inductive effect because it's through a sigma bond. There are no pi skeleton in an alkyl group. So this is an example of an electron donating group that is donating electronic charge to the benzene ring through an inductive effect. Resonance effects, those are related to the pi skeleton. So it's not the sigma bonds, it's the pi skeletons. And it's the ability that in some structures, some functional groups that can interact with their pi bonds with the pi skeleton of the benzene ring. And you've got here an example of, for example, a carbonyl group, cyano group, or a nitro group they have that inductive effect we studied before, but they also have this resonance effect. They can add to that pi skeleton that the benzene ring has. And if you look at the separation of charges, again, you have these carbons with a partial positive charge, the oxygen or the nitrogen with a partial negative charge. In this case, you have a nitrogen that does have a proper positive charge. So they are withdrawing electrons from the ring, from the benzene ring. But that withdrawing of electrons happens through the pi skeleton. In some cases, you have groups like the halogens, the hydroxyl group, or an ether group, or an amino group. Again, they donate electrons by resonance effect. And in this case, they are donating electrons. If you think of, they have the electrons that can be donated. You have the oxygen, you have the halogens, and you have the amino group. They have this sort of electrons not using the bond that can cooperate, react. They can add to the electron charge of the benzene ring in that pi skeleton. So in this case, the electrons flow from the substituent to the ring. And the effect is the greatest at ortho and para position, and we will look a little bit into that in a later slide. And sometimes you have groups that can, well, sometimes both the sigma effect, well, you can have sigma and pi, you can have inductive effects and resonance effects in the same functional group. And sometimes they both add to each other, like for example in the case of the carbonyl group, and in others they go against each other. So on one hand, the halogens or the hydroxyl group or the ether group donate electrons through a resonance effect, and on the other hand, they withdraw electrons through an inductive effect, through the sigma bond. So those two effects contradict each other, and they kind of work against each other. Inductive effects are stronger than resonance effect. So it is the inductive effect that will determine the orientation, where a second or subsequent substituent will go into that group. In a chemical reaction, the stronger effect dominates. So for groups that can have both an inductive effect and a resonance effect, if they both act against each other, one is electron donating and the other one electron withdrawing, the inductive effect will be the strongest one and will determine where the second substituent goes in that benzene ring.